Right. In this video, we're working AP Pre-Cal homework 4.1, which is about exponential functions. So the first few problems for this is going to give you these four functions f, g, h, and j. And we're going to ask for each of the functions, what type of function is it, what are the y-intercepts, values of the functions, all sorts of stuff. Right, so I think I'm going to go in and for each of them just write growth or decay above it. The first one, f, is we're looking at the base of the exponential, the number that's getting taken to the xth power. And I think I might as well write in the general form of an exponential right up here, and that's going to be y equals a times b to the x. And we're saying if b is greater than 1, we're going to be showing exponential growth, and if b is less than 1, that'll be exponential decay. Okay, so on number 1, 2 times 4 to the x, 4 is bigger than 1, that's growth. 8 to the x, again bigger than 1, that's also going to be growth. 8 times 1/16 to the x, that's going to be decay because the base is a fraction, it's less than 1. So it's decay. And then over here, 4/9, again, 4 over 9 is less than 1, so it's going to be decay. Okay, when determining whether you're dealing with exponential growth or decay, all that matters is the base of the exponential, whether it's bigger than 1 or less than 1, and I guess between 0 and 1. But in this class, we only deal with exponentials that have base that's positive, so you don't have to deal with like -1 to the x power. All right, what are the y-intercepts of the function? I guess I'll just do that underneath. Okay, for the y-intercept, I'm going to plug in x equals 0, so f of 0 equals 2 times 4 to the 0, right? And, we have to be thinking PEMDAS here. We're thinking, okay, exponents before multiplication by 2. So 4 to the 0 is 1, and it's going to be 2 times 1, and that's going to be 2. So the y-intercept is 0 and 2, or just y equals 2, whatever you want to say. Okay, for g of x, we're going to find the y-intercept by plugging in 0, just the exact same. 3 times 8 to the 0 power, we're going to do the exponent before the multiplication. And so that's 3 times 1 is equal to 3. Okay, h of 0, let's see the pattern here. 8 times 1/16 to the 0 power. 1/16 to the 0 power is going to be 1. 8 times 1 is 8. Just really keeping in mind PEMDAS here. 4 times 4/9 to the 0 power. That's going to be 4 times 1, which is 4. All right, now f of 2. So I think the rest of these the whole rest of the page, we're just going to be plugging in directly to each of these functions. So it's f is 2 times 4 to the x. And I think what I might do is I might do all three of these right here that are f of x, just so I can keep the function straight. F of x equals 2 times 4 to the x. Okay, so f of 2, wherever I see 2 in the equation for f, or wherever I see x in the equation for f, I'm going to replace it with 2. So 2 times 4 to the second power, exponent before multiplication, 16 times 2 is equal to 32. Okay, f of -2. I'm going to do 2 times 4 to the -2 power. Okay, now 4 to the -2 power, this is what we need to be careful about. We haven't talked about this in a while. This is equal to 2 times 1 over 4 to the +2 power. This is what the negative exponent does. It turns something into a fraction, or if it's a fraction, it flips it. Okay, so 2 times 1 over 16. So that's going to be 1 over 8. And then f of 1/2 is going to be 2 times 4 to the 1/2 power. That's another one we're going to need to be careful with. Okay, the 1/2 power, that's like the square root. So I'm going to say this is 2 times the square root of 4. It's going to be real explicit here. And that's going to equal 4. G of x, start off with g of 2, and that's going to be 3 times 8 squared, and that's 3 times 64. Ooh, this is kind of near the limits of my ability to multiply, but 3 times 60 is going to be 180. 3 times 4 is 12. If I add 180 and 12, I'm going to get 192. I can do that. Okay, g of -1, that's going to be 3 times 8 to the negative first power. Or the negative first power is going to be 1 over that thing. So this is going to be equal to 3 times 1/8. That's just going to be 3/8. G of 1/3 is going to be 3 times 8 to the 1/3 power. Okay, the 1/3 power, that's going to be the cube root. Right, 3 times the cube root of 8, and that's going to be 3 times 2, which is 6. All right. H of x. H of 1 is 8 times 1/16 to the first power. And I think it's definitely good that we remind you that anything to the first power is just going to be itself. So that's going to be 8 times 1 over 16, so it'll be 8 over 16, and that's 1/2. H of -1 is going to be, we're just going to replace x with -1. Okay, we're going to be careful here. -1 power with a fraction. Okay, 1/16 to the negative first power, that's going to be 16 over 1. So that's going to be 8 times 16. So that would be 80 plus 48 is equal to 128. And got h of 1/4, so that's going to be 8 times 1/16 to the 1/4 power. 1/4 power is going to be the fourth root, so I need to take the fourth root of 1 over 16. About that, that's going to be the fourth root of 1, which is 1, divided by the fourth root of 16. Or you could think about what could you take to the fourth power to get 1 over 16? Anyway, it's a half. So that's 8 times 1 over 2, and that's equal to 4. So no, it's not on screen, but there you go. All right, and then the last few of them is j of x equals 4 times 4/9 to the x power. So j of 2 is going to be 4 times 4/9 squared. If I square 4/9, I'm going to be squaring the 4 and the 9 because I'm going to multiply 4 over 9 times 4 over 9. So that's 4 times 16 over 81. Okay, that's not going to be able to simplify, so I'm going to multiply 4 times 16. That's 64 divided by 81, and that's all I can do with that. Okay, j of -1. I'm glad we're getting this practice in. This is important. So 4/9 to the negative first power. And remember, the negative first power flips the fraction, so that's going to be 9 divided by 4. So 4 times 9 is 36 divided by 4 is 9, or you could just cancel off the 4's, and either way, that's going to be 9. And then the last one here is going to be 4 times, alright, that's what this one was building up towards here. The 1/2 power, that's the square root. If we take the square root of 4 over 9, that's going to be the square root of 4 divided by the square root of 9. We can do that. So that's 4 times the square root of 4/9, and so that's going to be 4 times 2 over 3. That's 8/3. Okay, this next set of problems just continues to go with the same functions. Okay, that's good. Okay, so we're going to do some transforms. Okay, so that's good. So f of x vertically translated up 4. Okay, so that would be, starting from f of x and going to up 4 is adding 4 on the outside. So plus 4. This is something that we talked about back at the very beginning of the course. I think it was 0.4 or something like that. Definitely in unit 0, where we were talking about basic transforms, translations, and vertical dilations was what we've talked about so far in this class. So if I do f of or not f of 4 plus 4, that was a mistake. I didn't mean to write that. F of x plus 4. So we're going to copy down f of x. So that's 2 times 4 to the x. And then we're going to take it and add 4 to it on the outside. So that's f of x vertically translated up by 4. G of x vertically dilated by a factor of 3, that's where we're going to multiply the output values by 3. So that's going to be 3 times g of x. Okay, so g of x is equal to 3 times 8 to the x. I'm going to take this and multiply it by 3. Okay, and what we can do here is going to be 3 times 3 times 8 to the x. And if 3 was a factor of 8, maybe we could do something more with this with exponent properties. That's what we're going to talk about more next time. But for now, what I'm going to say is all we can do is multiply the 3 by the 3 that's right there and say this is 9 times 8 to the x. For h of x horizontally translated left by 2, okay, that's where we're going to replace the input values. So we're going to start with h of x, and then we're going to replace all the x's with x plus 2 if we're moving to the left by 2. Okay, if we were moving to the right, we would subtract 2. But we're moving to the left, so we're going to replace x with x plus 2. And it's not like that. Keep messing this up. H of x plus 2. Alright, so h of x is equal to 8 times 1/16 to the x power. And if we're going to replace that with x plus 2, then we just need to get rid of x and replace that with x plus 2 right there. Okay, so that's, and for us, that's going to be a good place to stop. Next time, we're going to investigate what that does to the graph, or what else it does besides horizontally translated left by 2. What we can do with exponent properties to show that other things are happening simultaneously. All right, j of x horizontally translated right by 1. That's going to be where we replace x with x minus 1. All right, so j was 4 times 4/9 to the x. Okay, but I'm going to be replacing x with this x minus 1. So get rid of that, replace it with x minus 1, and that'll be perfectly fine. 5 asks us to use limit notation to express the end behavior of f, g, h, and j. All right, so I'm just going to kind of zoom in on each of these and write in the limits. So to describe the end behavior of this function, we're interested in the limit of the output values as x approaches infinity and negative infinity. And so to start with 2 times 4 to the x, as x approaches positive infinity, you've got 2 times a positive number taken to a really large positive power. That's just going to get really big. You can make that as big as you want it by choosing a large enough exponent, right? So we're going to say this limit is infinity. And then the limit as x approaches negative infinity of 2 times 4 to the x, this one's going to equal 0. Okay, and we need to just know that, and I would prefer that you just know it pretty quickly, that as x approaches negative infinity, a positive number that's greater than 1 to that power is going to go to 0. I think 2 ways I would remind you of that, one, okay, the graph of 2 times 4 to the x, this is just pretty standard exponential growth. It's going to have a y-intercept of 2. It's going to look like that. Okay, and it has that horizontal asymptote of y equals 0, and that's the limit of the function as x approaches negative infinity. Okay, you could also think about as x approaches negative infinity, think about 2 times 4 to the, x power. And think about when x goes I don't know, negative 10 even. Okay, if x was negative 10, negative 100, negative 1,000, negative million, that's going to become, with a negative exponent, 2 times 1 over 4 to an increasingly large positive power, so 10 in this case. But if I had thought about 4 to the negative 100, that would be 1 over 4 to the 100 power. I've got something where the numerator is staying constant and the denominator is growing without bound. Okay, that's the type of thing that goes to 0. We saw that in the last unit. Okay, so that's another reason why this works. I think probably in the video and in the lesson a showed a more algebraic way to show that the limit goes to 0, but we don't need to do that here. All right, G is almost exactly the same. The numbers are different, but they're both positive and greater than one. So, like the end behavior is going to be the exact same. As x approaches positive infinity, 3 times 8 to a really large positive power, that's going to go infinity. And as x approaches negative infinity, we're going to be taking 3 over 8 to a really large power, so that's going to approach 0. I'm just going to copy those in and move on. Here, this one, h represents exponential decay. So, oh, whoops, I just kind of moved over the writing I had earlier. H represents exponential decay, so as x approaches infinity, right, we're going to have a situation 1 to the x is always going to be 1 for any power of x. And the denominator is going to be growing because we're also going to be taking 16 to the x power. So that's going to be getting really big, and then the 8 is just going to stay multiplying there and not really actually impact the total all that much. And so what we're saying is that as x approaches infinity, 1 over 16 to the x, that's going to be approaching 0, and 8 times 0, well, that's still 0. Okay, and then over here, as x approaches negative infinity, that's going to, for any negative value of x, this is going to flip the fraction. It's going to be some positive power of 16 over 1. And that's going to be the type of thing that grows really large, right? If we're taking 16 to larger and larger powers. So as x approaches negative infinity, 8 times 1 over 16 to the x, that's going to approach positive infinity. And you could also think about it, this is an exponential decay curve, and those kind of look like that. So x is approaching 0, or y is approaching 0 as x approaches infinity, but on the back end of the curve, we're going uphill, we're going increasing without bound. Last one is the same. It's an exponential function that's showing exponential decay, and so it's going to have the same behavior as x approaches infinity. 4 times 4 over 9 to the x is going to approach 0, and as x approaches negative infinity, this thing is going to approach positive infinity. All right, with this next one, we're going to be given a common ratio and a point that's on the graph. So we're really just going to be kind of like fitting it back to the general form of the exponential function that they give us for AP Pre-Cal. Okay, so the common ratio, that's the thing that we're multiplying each time x increases by 1. And so that's going to be b. I think that's important. I think there's some kind of language on the test or some multiple choice question that they've seen that you need to be able to conflate the word common ratio here and like this value of r with b. Okay, the thing that we're multiplying by each time that x increases. Okay, that's enough emphasis on that. And so I'm going to say r equals 2, so that means b equals 2 is my first thing. And it goes through the point 3 and 8. So f of x equals a times b to the x. And we now know that b is equal to 2. Okay, then we're going to plug in f of 3 equals 8. So 8 is equal to what I get back when I plug in 3 for x, 2 to the third power. So 8 equals exponents before multiplication, so a times 8. 8. And so if 8 equals a times 8, a is going to need to equal 1. Okay, for the second one, we're going to decode this, say, all right, the value of b in that equation is equal 3, so we've got f of x equaling a times 3 to the x. F of 2 equals 1/2, so 1/2 equals a times 3 to the 2. If 1/2 equals a times 9, I would divide both sides by 9 to solve for a, and I'd get a as 1 over 18. So I'm just going to approach this one the same way. So some number times common ratio to the x power. Okay, we know that f of 4 equals 8, so 8 equals a times 2/3 to the 4th. Wow, that's kind of big numbers. Okay, so 8 is going to equal a times 2 to the 4 is 16, divided by 3 to the 4 is 9 times 9, that's 81. Okay, that's fine. Okay, so I can multiply both sides. Ooh, yeah, but I'm gonna not actually multiply 8 by 81, right? So I can save the arithmetic on myself. I'm gonna say, all right, a is gonna be, I'm gonna multiply both sides by 81, and then divide both sides by 16. That 8 over 16 can be simplified to 1 over 2. So that's going to be 81 halves. And then I've just been solving for A, and that, honestly, that's a mistake. I saw that happening. On a recent calculus test where they were doing separation of variables, something you'll encounter next year in your AP calculus class. But they were just like solving for the value of C, but not reporting the function that was the answer. And it's actually very similar to the process we're going through right here. Is kind of just backfitting to a point. They have to do a little bit of calculus first, but our presented answer here should be f of x equals 1 times 2 to the x. And I'll even throw a box around that. Over here, a equals 1/18th, f of x equals 1/18th of 3 to the x. That still shows exponential growth, even though that a value is less than 1. That just means the y-intercept is going to be pretty close to the x-axis. Okay, over here, this one I got a equals 81 halves, so my presented answer should be f of x equals 81 divided by 2 times 2/3 to the x. And the fact that 81, is that right? Yeah, that's right. The fact that that one has a shared factor with the 3, we're going to ignore that for now and investigate what else we can do with that next time. Here, r equals 1/2, so that's b equaling 1/2. F of x will equal a times 1/2 to the x. F of -2 equals 6, so 6 equals a times 1/2 to the -2. Okay, so that's going to be the negative power will flip the fraction, 2/1 to the +2 power. 2 squared is going to be 4, so 6 equals 4a, and a will be 4 divided by 6. It's 2/3. Okay, and then my answer is going to be f of x equals a is 2/3 times b to the x, where b is 1/2. And again, that 2 there, we could simplify a little bit on that, but the way that we do that, we need to talk more about exponent properties in a way that we didn't in the lesson today. So we're just going to do that next time. Now we've got, given the table, write an equation that models the exponential function. Is your function a growth or decay? All right, so an equation is going to be, I'm just going to say, we're looking for y equals a times b to the x. Okay, b is the common ratio that we get when we multiply, or that the output values get multiplied by when we increase the input values by 1. And a is going to be the y-intercept. And for the 2 on the left, we're going to be able to just read that off real quick. And so we're going to want to do that. Right here, we're seeing a equals 2/9. Over here, 0 and 3/2, I'm going to say a equals 3/2. Okay, and then to find b, we think about what are we multiplying by each time we increase x by 1. So I'm kind of just looking over here at the table for f and looking for 2 that are easy, because if it's an exponential function, it should be consistent, right? X is increasing consistently by 1 each time, so I should see the same multiplier each time. And 2 to 6, that's multiplication by 3. It might be good to verify with the other ones that that's working, but yeah, that looks like it to me. So b is going to equal 3, and then I can conclude that f of x is going to equal a times b to the x. We can write it like that, right? Because of PEMDAS. You have to do the exponent before the multiplication by 2 nines. Okay, and then on C, this one was pretty similar, so I think about, okay, what am I multiplying when I go from 3/5 to 6/25? Okay, it looks like to me I'm multiplying by 2 on top and 5 on bottom, so I'm going to say that b is 2/5. Now that's interesting that I'm going from 6/25 to 5/52. That's gotta be wrong, right? 5. So 12/125. I can't imagine how that's 5/52. 3/2.
times 2 over 5, yeah, that would give you 3/5 times 2 over 5. Yeah, I'm going to assume that 5 over 52 is like not quite right. And that b is equal to 2/5. I'm not sure about that. Maybe it does simplify in a way that I'm just not seeing, but I'm going to say, all right, h of x here is going to equal a times b to the x. I'm not going to try to simplify that any farther. All right, for the two on the right, we're just going to have to use the 2 points and set up a system. Okay, and then you might be doing this a different way, and that's totally fine. You can solve this type of problem however you want. There are definitely other ways. But I'm going to go over here and I'm going to say I'm looking for y equals a times b to the x. So I'm going to use just the first 2 points, x equals 1 and x equals 2, because those are going to be the easiest two values. So I'm going to plug those in. So y equals 2 when x equals 1. Maybe I'll use red over here. So x equals 1, y equals 2 gives me the equation 2 equals a times b to the first power, which is just b. And then if I use x equals 2 and y equals 1/2, I'm going to have 1/2 equals a times b squared. And something that I never had cause to do this in my Algebra 2 class last year, taught it the whole year, never needed to solve a system this way, but one thing that we can do here is we can divide one equation by another, and that's what we're going to do. So I'm going to want to take the second equation and divide it by the first so I can divide the a's away. Okay, so what I'm going to say is I'm going to kind of combine these and say that, all right, so 1/2 is equal to a times b squared. If 2 is equal to a times b, then I can divide both sides by, the two things that are equal. So divide by 2 and divide by a times b. It is provided that we're not dividing both sides by 0, which we clearly are not. Okay, so I might, move the equality down over here, but that's what we're doing is we're dividing one equation by another. Just a different way of solving a system. And we're going to eliminate those a's, eliminate 1 power of b, and we're going to get 1/2 divided by 2, that's 1/2 times 1/2, that's 1/4, is equal to b. And then we're going to plug that back in, maybe to this equation right here. And we'll say, all right, 2 equals a times 1/4. So what times 1/4 would equal 2? That would be 8, so a equals 8. And I can write my equation. G of x is equal to a times b to the x. And if you got a different way to solve this problem, I'd be really interested to see it. So just like, come show me, bring it to me in class sometime. I'd be interested to hear about all the other ways that you can do this one, besides what I'm going through right here with the system. All right, so I'm going to do the same thing, set up the system, y equals a times b to the x. I might go a little faster this time. I'm going to use -2 and -3 because those look like the smallest and easiest to deal with numbers. So x equals -2, y equals 9/2. So that means 9 over 2 equals a times b to the -2. And then I'm going to go over here and say, all right, with x equals -3 and y equals 27 over 4, say 27/4 equals a times b to the -3. All right, I don't love the look of doing this one algebraically by, dividing one equation by another. So I think I'm going to go in and I'm just going to do a little bit of work like I did over here and just look and find b from the ratio. Okay, so I'm thinking about what am I multiplying by each time when I go to the right by 1, when I increase x by 1. So it looks like I'm multiplying by 2 on top, right? Because the denominator is getting halved. So I think that the ratio is going to be 2 on top and maybe 3 on bottom. This is kind of a weird sequence of fractions where it's, the actual values are getting smaller. But I think eventually it would just like kind of pivot and the denominator would start getting bigger, numerator small. I don't know. No, that's what's happening right now. I don't know. Looks to me like the ratio is 2/3. Yeah, I feel good about that. So I'm going to use that and, just kind of plug that in there. and say, all right, 9 halves is going to equal a times b to the negative 2 power. And I guess you could find the value of a, knowing it's the y-intercept, by just going and multiplying by 2/3 twice, but that's essentially what I'm about to do over here. 9 halves equals a times 3 halves squared, right? Deal with the negative exponent. Then I'm going to say 9 halves equals a times 9 over 4. So think about what would I multiply there to make the denominator go down by half. That would be multiplying by 2. So I'm going to have a equals 2, and then my equation will be h of x equals a times b to the x. All right, this next problem type here asks for you to write an equation for the exponential function that passes through the given 2 points, and this is where we're saying the exponential function has to be like the AP pre-cal type where it's y equals a times b to the x. All right, so if we're over here, they gave us a y-intercept, that's really nice. So 0, 6, that means that the value of a is going to be 6. So I'm going to each time write in that I'm looking for y equals a times b to the x. All right, so I got a equals 6. And then 3 and 2/9. So 2/9 is y equals a 6 times b to the third. Right? Yeah, b to the x. Okay. So then I'm going to, I guess, divide both sides by 6. Okay, yeah, so, oh yeah, it's going to work out just fine. Okay, so I'm going to divide both sides by 6, and I'm going to get 6 times 9 is 54. 2 over 54 equals b cubed. If you're like me, you're thinking like, how am I supposed to find the cube root of 54? But then you remember, hey, this is something we can reduce. So b to the third is equal to 1 over 27, and that is something we can take the cube root of. Okay, that's going to be the cube root of 1 divided by the cube root of 27. Okay, so b is 1/3, and my exponential function is going to be y equals a times b to the x. So next one here, I'm gonna do this one by setting up a system. I think that's the most like dependable way and very algebraic. And so I'm gonna say, all right, using x equals 1 and y equals 6, 6 equals a times b to the first power. And then 3 and 54 means 54 equals a times b to the third. And then I'm going to divide the second equation by the first. So 54 over 6 is going to equal a times b cubed divided by a times b. So I'll get that b squared equals 54 over 6 is 9. Because I can cancel off the a's, and I can cancel off one of the powers of b, and I can simplify 54 over 6. Okay, and if b squared equals 9, and in this class we're interested in bases that are positive, we're going to say, all right, that means that b is going to be equal to positive 3 in this case, because we're dealing with the exponentials. So y equals a. Did we figure out what a was? No, we haven't done that yet, but 6 equals a times b, so that means a is going to need to equal 2. So I'm going to use that, show me that, and so y equals 2 times 3 to the x. All right, this one, 1, 4, and 4, 32 over 27. All right, this one, you can see that having x equals 1, that's pretty beneficial for the technique I'm using. So I keep going with that. But we should see like b cubed equals something because we took 3 steps from x equals 1 to x equals 4. So we should be able to figure out b that way. And if that's how you're figuring out b, then good for you. It's exactly the same as what I'm doing here. So y equals 4 when x equals 1. And y equals 32 sevenths when x equals 4. Whoops. B to the 4. All right, and so I'm going to divide the second equation by the first. A times b to the 4 divided by a times b. And if I've got 32 over 7 and I'm dividing by 4, that's like multiplying by 1/4. So I could simplify that and make that 8 divided by 7. I'm going to do that. So that's going to cancel off a's, 1 power of b, so that's going to be b cubed. Okay, now 7, is that right? Oh, no, I didn't copy it right. 27, all right, so that's going to be all messed up. Is that just going to be 8 over 27? Okay, that's not going to, I didn't simplify it in any meaningful way, I guess. Okay, so I guess, oh, just the 32 divided by 4, it didn't impact the number that was down there. Okay, yeah, so we're good. So we're taking the cube root. So b equals the cube root of 8 divided by 27. That's going to be the cube root of 8 divided by the cube root of 27. And then 4 equals a times b, so 4 equals a times b. So we're going to multiply by 3, divide by 2, get a equals 6, and then our function is y equals a times b to the x. Okay, I guess that's it for that problem. Yeah. All right, now we're going to write an exponential expression that models a situation where a and b and c are all constants. So what is 4 tripled 13 times? I like this one. Okay, so we're going to start with 4, and then we're going to triple it. Well, tripling it once would be like multiplying by 3. Multiplying by 3 twice would be tripling twice. Okay, so if we tripled 13 times, we're going to be having a bunch of 3's, and something that we could write, a little shorter as 3 to the 13th power. So, they said a times b to the c, a equals 4, b equals 3, c equals 13. Okay. 20 halved 20 times. Okay, so I'm going to half something, I'm going to multiply it by half. Okay, and if we did that 20 times, I could put an exponent of 20 on the 1/2. And so I'd say a equals 20, b equals 1/2, and c equals 20. This one here, I've got a bunch of 2/3s and then a 30. So I'm going to hold the 30 off to the side. And I'm going to count the number of 2/3 fractions I have. So that's 1, 2, 3, 4, 5 of them. I'm going to write that as 5th power. I'll just copy down exactly what I was given on print on my paper. So I've got 30 times 2/3 to the 5th is 30, b is 2/3, and c is 5. Over here, okay, I've got a bunch of 3's and 1/6. So I'm write it as the constant, and then the thing getting taken to the cth power, that's the repeated number. So that's going to be 3. Count the number of factors of 3. I'm counting 1, 2, 3, 4, 5, 6 of them. So I've got a is 1/6, b is 3, and c is equal to 6. All right. Now, number 10, we've got an infectious disease doubling every week. City started with 100 infections. How many are infected after 5 weeks? Okay, doubling every week, so that's going to be 100 that we started off with, and then after 1 week it doubled. After the second week it doubled twice, and then we put an exponent of 2 up there. After 5 weeks it's going to have an exponent of 5, okay, and that's going to be 100 times 2 to the 5th, 2, 4, 8, 16, 32. And so 100 times 32, that's going to be 3,200. Savings account grows at 4% per year. If you started with $10,000 in the account, so you're starting with 10,000, how much money is in the account after 15 years? Okay, so multiplying by a 4% growth, that's going to be 1 plus 4% is 0.04. And then After 15 years, I guess assuming compounding once per year, we're going to take that to the 15th power. And, without a calculator, we're not going to be able to do anything else with this. But I don't feel like bringing in the calculator right now, so I'm just going to leave that there. Okay. A car was bought for $100,000, depreciating 15% per year in value. How much is it worth after the 8 years? All right, so I'm going to go over here and say 100,000 is what I'm starting with. And then I'm going to multiply by, okay, depreciates is going to be exponential decay. It's going to be decreasing in value. So I'm going to start with 1, and then I'm going to subtract 15%. So 15% is 0.15. So 1 minus 15 cents would be 85 cents. Oh, whoops, and I need to take this to some kind of power. How many years after 8 years? So it's going to be to the 8th power. So that's 100,000 times 0.85 to the 8th power. I guess I could have rewritten this as 10,000 times 1.04 to the 15th, but either way, those are calculator ready. So, in the absence of like having a calculator right there, you could, if you had one right next to you as you were working homework, you could type those in and see what the actual number is. But I don't think that that's as important as being able to generate that expression. That's what I really need to be able to do. So the radioactivity half-life of tritium, I don't even know what that is. I'm definitely not a chemist though, is approximately 12 years. If you start with a 1 gram sample, how long until 25% remains? This one's tricky. Okay, this one is actually easier to do just thinking about it than it is to like try to set up an equation. But the half-life is 12 years. So if we wanted to do like half-life stuff, the formula is like the, amount is equal to some like starting amount. So some A. And then it's like half-life to the time divided by like the half-life they give you. So if you start with a 1 gram sample, A would be 1. So it'd be like Y equals 1 times 1/2 to the, okay, oh, T divided by, they said that half-life was 12. So T would be measured in years, and we would do T divided by 12 because that would give you the number of half-lives. But that's just what we need to think about, is like how long until 25% remains. Well, that would be when we were multiplying by a fourth. So we need the exponent to be 2. That's what you need to think, is that 25% would be when you got cut in half twice. So that would be after 2 half-lives. So, that would be 2 times 12 is 24. More algebraic way to look at this would be that T over 12 needs to equal 2, and then multiply both sides by 12 and get that T equals 24. All right, and that's all the problems we've got in this problem set for you. So that's going to be all. Thanks for watching.